Dawn, orbiter probe of Vesta and Ceres. Project profile and mission. Dawn is a now retired space probe. Launched by NASA in 2007, Dawn orbited the two largest objects in the asteroid belt, Vesta and Ceres, for a total mission length of 11 years. The mission was managed by NASA's Jet Propulsion Laboratory, with major contributions from the United States, Germany, Italy, and France. Dawn was created to address a simple question: what was happening at the dawn of the solar system? But what does it actually mean to address a question this broad? We can begin to break it down by asking, how do planets form and what governs their evolution? This leads to two main mission objectives. One, to understand the conditions under which protoplanetary objects form. This leads to a better understanding of how terrestrial planets form. And two, to better understand what drives the evolutionary paths of rocky bodies by comparing and contrasting different evolutionary outcomes. Specifically, we are interested in how both water and physical size shape evolution of an object. We've chosen the mission objective. Now, what objects will help us achieve it? Protoplanets can provide an insight into the formation of larger objects, such as terrestrial planets. The current theory on planet formation postulates that larger objects formed through accretion via collisions with several smaller bodies. Protoplanets represent a snapshot into the steps of planet formation. The two largest protoplanets in the inner solar system are asteroid belt objects, Ceres and Vesta. Studying two objects provides the opportunity to compare and contrast their individual formation and evolution. Ceres and Vesta are similarly located in the solar system, yet have very different evolutionary paths. Located 2.8 AU from the Sun, Ceres is the largest object in the asteroid belt, both by mass and radius. Ceres is the only known dwarf planet to be found inside Neptune's orbit. This makes it uniquely interesting for studying the transition from rocky to icy bodies. Even before the Dawn mission, there was evidence that Ceres contained subsurface water ice. Ceres has a low density, which indicates it contains ices, and water vapor has been seen above the surface. Located 2.4 AU from the Sun, Vesta is slightly closer to Earth than Ceres. Vesta is the second largest object in the asteroid belt. Vesta is a rocky protoplanet and thus interesting when researching the formation of terrestrial planets. Vesta does not have the designation of dwarf planet as it is not round under its own gravity. In contrast to Ceres, Vesta is dry and rocky, showing no signs of ices. With objectives determined and targets chosen, we are now ready to build the spacecraft. The technology that went into Dawn spacecraft is just as important as the data it collected and the conclusions which were drawn. None of the scientific successes would have been possible without the technological successes and innovation. Regardless, from the perspective of a planetary scientist, it is important to understand how data is taken and how instruments are designed and chosen for the specific mission. Both money and space are limited, so instruments must be able to accomplish the mission objectives exactly with no superfluous equipment. These two images show the scale of one wing of Dawn's solar array. The main body is visible in the background of both images. On the left, you can see the panels being folded into the transport configuration, and on the right, you can see the solar array fully extended. The framing camera. This instrument is the German contribution to Dawn. It has 7 bandpass filters, which can be used for spectrometry, and a clear filter for broadband imaging and navigation. The bandpass filters can be used to study the surface reflectance, which in turn leads to information about the topography and composition of the surface. For redundancy, there are 2 identical framing cameras on board Dawn. Each of these cameras has a mass of 5.5 kilograms. Here's a diagram of the framing camera. Light first passes through a refractive telescope, then through one of the 8 filters on the filter wheel, before finally landing on a CCD which is cooled to -60 degrees Celsius. The visible and infrared spectrometer. This instrument is the Italian contribution to Dawn. It was designed to analyze the reflected and emitted radiation from the surfaces of the asteroids. It is sensitive enough to determine the composition of rocky surfaces and to identify minerals that may have formed in the presence of water. This instrument weighs 9.3 kilograms. This is a diagram of the visible and infrared spectrometer. I believe the accordion-like design with many mirrors is to help the instrument fit in a small area, as space is at a premium on the spacecraft. The gamma ray and neutron detector. This is the instrument contribution from the United States. It is sensitive to gamma rays and neutrons, which are emitted by radioactive sources or created by cosmic rays striking the surface. It can detect the abundances of elements which would be present in ices. This returns to the objective of determining the role of water in the formation of rocky bodies. Here is a diagram of the gamma ray and neutron detector. Note the very different design for detecting gamma rays and neutrons versus detecting optical and infrared photons like the framing camera. Entering a new era in space travel. Dawn was designed to be groundbreaking. Dawn would become the first spacecraft ever to orbit two bodies. On its way to Vesta, Dawn broke the velocity change record when it exceeded the previous record held by Deep Space One of 4.3 kilometers per second. Dawn reached a total velocity change of 11 kilometers per second. This velocity change is due only to Dawn's own propellant system. Neither of these accomplishments would have been possible without the ion propulsion system. The ion propulsion system allowed Dawn to escape the orbit of Vesta. Ion propulsion works by feeding xenon into a chamber where it is ionized through collisions with electrons. The ionized xenon is then accelerated by an electric field between the two grids. Before leaving the spacecraft, the positive ion gas is neutralized to prevent it from being attracted to the spacecraft. Thrust is generated through the conservation of momentum. Dawn has 3 ion thrusters total. This image shows when the ion propulsion system is activated in blue. Note, Dawn activates its ion thrusters when moving between objects, not when it is in orbit around an object. Dawn achieved an incredible 6 years total of powered flight. Objectives determined, targets chosen, and spacecraft built, we are now ready for launch. The Dawn spacecraft launched from Cape Canaveral Air Force Station, Florida, on September 27, 2007. Here is an animation of the path traveled by Dawn. This is a view centered on the Sun, with Earth being on the innermost shown orbit, and Ceres on the outermost. Dawn is the pink line. We can see the spacecraft leaving Earth. Here we can see Dawn using Mars for gravity assist. Now we see Dawn in orbit around Vesta. When Vesta and Ceres are in their closest approach, Dawn jumps from Vesta to Ceres, where it will now remain in orbit. Our space probe is launched. Let's see what we discover. Nearly 4 years after launch, Dawn has arrived at its first target, Vesta. This sequence of images were taken on its approach. Here's the trajectory of Dawn around Vesta. Note the speed and the altitude along the bottom. Dawn goes from a surveying orbit to its first high-altitude orbit, to a low-altitude mapping orbit, and then back to its final high-altitude mapping orbit. And now Dawn uses its ion thrusters to escape the gravity of Vesta. Before the Dawn mission, many of the surface details of Vesta were completely unresolvable. Dawn revealed the surface to be heavily cratered with several interesting and surprising features. The 2 largest craters on Vesta are Rhea Silvia and Venonea. Rhea Silvia is the largest impact crater on Vesta. It has a diameter nearly 90% the diameter of Vesta itself. The impact which created Rhea Silvia likely excavated about 1% of Vesta's volume. Venonea is the second largest crater on Vesta. It is approximately 70% of the diameter of Vesta itself. Unlike Rhea Silvia, it was only discovered during the Dawn mission. These ancient craters are much larger than expected, suggesting that there were more large objects in the early solar system than originally thought. This indicates that planetesimals were large objects themselves, rather than being built over time by the accretion of smaller objects. The collisions that created these large craters played an important role in shaping Vesta's evolution, and the craters themselves reveal material that would otherwise be hidden under the surface. This is an animation showing the rotation of Vesta using images taken by Dawn. In addition to the numerous craters, one of the most striking features are the deep troughs in the equatorial region. What could have created such prominent chasms? The troughs on Vesta are very unusual for an asteroid and cannot have been created by simple collision, like those which created several of the smaller craters. A large collision, such as the collisions which created the Rhea Silvia and the Venonea craters, could have created the troughs, but only if Vesta is differentiated into core, mantle, and crust layers. Each of these layers would have a different density and would react differently to the force of the collision, ultimately causing the surface material in the equatorial region to slide apart. This is very similar to the tectonic process which creates troughs known as a graben. Graben have been identified on the terrestrial planets and on some moons. If Vesta was indeed differentiated, it would be much more like a planet or a moon than an asteroid. Howardite, eucrite, and diogenite meteorites. HED meteorites are a subclass of achondrites. Achondrites are thought to originate within the crust of bodies that experienced differentiation. Bodies which experience differentiation go through a period where they are molten and much of their iron sinks to the center. Confirming the parent body for these meteorites therefore tells us about the evolution of that body. Achondrites account for about 8% of all meteorites, and 2/3 of those are HED meteorites. Because of Dawn, Vesta was confirmed to be the parent of the Howardite, eucrite, and diogenite meteorites. This confirmation was made by comparing the composition of the meteorites to the composition and mineralogy data taken by Dawn, using the VIR and GRAND instruments. The two images shown here are thin slices of diogenite meteorites recovered in Antarctica. The colors are due to different minerals present in the rocks. These rocks were likely excavated from the crust of Vesta during the large collision which created the Rhea Silvia crater. Pre-dawn, images taken by the Hubble Space Telescope indicated the presence of basaltic flows, which are produced from a molten core. It was not until the Dawn mission could the gravity field of Vesta be measured and the presence of basaltic flows confirmed. Dawn found indications of an iron core. This supports the differentiation model suggested by the equatorial troughs and the HED meteorites. Together, this implies that differentiation could be much more common in the evolution of large protoplanets than was previously thought. On the side, the top image is of the topography of Vesta, and the lower image is a map of the gravity field. Troughs, HED meteorites, and an iron core. Evidence now points to Vesta being differentiated, just like the terrestrial planets. And differentiation may also be much more common in the evolution of large protoplanets than was previously thought. But that doesn't mean Vesta and other large asteroids get the designation of planet quite yet. Vesta seems to be something intermediate between an asteroid and a planet. We've answered some questions and surely thought of many more, but now it's time for Dawn to leave Vesta and head to Ceres. After 1 year of orbiting Vesta, Dawn makes the 3-year trip to Ceres, arriving on March 5, 2015. This is Dawn's first glimpse of Ceres. Here is a short animation of the trajectory of Dawn around Ceres. Note the speed relative to Ceres and the altitude relative to the surface along the bottom. Note how it goes through several orbits, including rotation characterization, surveying, high altitude mapping, and low altitude mapping. As with Vesta, Dawn was expected to reveal surface features on Ceres that are otherwise unresolvable. But in the case of Ceres, what wasn't found was more interesting. Ceres was thought to be heavily cratered like Vesta, as they are at similar locations in the solar system. but as dawn approached, it became clear Ceres is not as heavily cratered as expected. Some unanticipated process occurred on Ceres to erase the largest impact craters. Like with Vesta, Dawn confirmed Ceres is partially differentiated using measurements of its gravitational field. A deformable layer of ices and salts, perhaps in liquid form, could cause features on the stronger outer layer of rock and salt and ice to relax on a long timescale, causing impact craters to smoothen out. This suggests that ices have a significant effect on topography. Impact craters or no, Ceres does have several interesting surface features discovered by Dawn. The surface of Ceres contains several bright spots. These bright spots are caused by deposits of salts on the surface. Salt deposits are thought to form as brines reach the surface and crystallize. Using the VIR instrument, Dawn found the bright spots to be mainly composed of sodium carbonate, which requires water to form. This suggests that Ceres has had recent hydrothermal activity. This image shows the Occator crater, an impact crater containing the brightest bright spot on Ceres. But sodium carbonate wasn't just found in craters. In 2015, Dawn discovered the presence of a cryovolcano, now known as Ahuna Mons, on Ceres. Ahuna Mons is the largest and youngest mountain on Ceres, and the closest cryovolcano to the Sun that has been discovered. A cryovolcano is a type of volcano which erupts volatiles such as water and ammonia, and they are typically found on the icy moons of outer planets. Like all processes, cryovolcanoes require an energy source. For many icy moons, this comes in the form of tidal heating. But for Ceres, the energy must come from elsewhere. Ceres is a small, cold body that should have cooled quickly after formation. But the recent cryovolcanic activity suggests that Ceres did not freeze as quickly as expected. It is now thought that salts extend the geological activity by depressing the freezing temperature of water and allowing water to remain liquid under cold conditions. Given that features on the surface of Ceres relax relatively quickly, Ahuna Mons must have formed in recent geological times. This would suggest that Ceres is still geologically active or was very recently. On the left is a short false color animation which shows the water abundance of Ceres. The abundance of hydrogen was determined using the Grand instrument, and the assumption has been made that all hydrogen is in the form of H2O. In reality, only some of the hydrogen is in the form of water ice, and the rest is in hydrated minerals. Nevertheless, the abundance of ice is greatest near the poles. On the right, bright blue dots indicate regions in permanent shadow. These regions remain very cold, allowing water ice to be stable on the surface. Dawn found several landslides on Ceres. About 20% of craters larger than 10 kilometers in diameter have some sort of landslide associated with them. The shape of these features gives clues to the composition and conditions under which they formed. Landslides on Ceres share features depending on the latitude in which they formed. On the right is an image of a characteristic high-altitude landslide. The large, lobed toe is indicative of non-Newtonian flow due to high ice content at the poles, allowing it to overcome friction. On the left is an image of a characteristic low-altitude landslide. These landslides have a sheeted appearance, which may indicate the force of the impact heated the surface material, causing it to fluidize. These images were taken at a low mapping out orbit using the framing camera. Bright spots and cryovolcanoes are not the only interesting thing found on the surface of Ceres. Organic compounds such as ammonia were found to be abundant on Ceres. These organic compounds likely formed in Ceres' interior, possibly within a subsurface ocean. This is a false color image taken using the framing camera and the VIR instrument, showing organic compounds in red. Organic compounds such as carbon and ammonia are crucial for life on Earth, making Ceres an interesting subject for future studies in the development of life. But of particular interest to our mission objectives is the presence of ammonia. Ammonia is a volatile compound that is more abundant in the outer solar system. The distribution of ammonia on Ceres suggests that material from the outer solar system was incorporated into Ceres during its formation, or Ceres itself formed in the outer solar system and migrated inwards. This is evidence that significant shuffling events occurred in the early solar system. Dawn is a success. We've accomplished our mission objectives. We found that ices and salts have a significant effect on the evolution of an object. Not only can they cause the topography of an object to smoothen, they can also extend the period of geological activity in water-rich bodies. We also found evidence that significant shuffling events occurred in the early solar system, resulting in ammonia-rich body like Ceres moving from the outer solar system to the asteroid belt. In the fall of 2018, Dawn ran out of fuel needed to orient itself towards Earth for communication and to orient its solar panels towards the Sun for power. When communication was lost, the mission was officially ended on November 1st, 2018. Dawn will remain a satellite of Ceres. Dawn is not sterilized and cannot be allowed to come in contact with the surface of Ceres under planetary protection protocols. Ceres may harbor or may have harbored conditions of interest for those who study the development of life. Crashing the probe would risk destroying those conditions or evidence of those conditions. And in addition, it has the chance of introducing Earth microbes to Ceres. Returning briefly to the mission objectives, we set out to learn what was happening at the dawn of the solar system. By 1, better understanding the conditions under which protoplanetary objects form, and 2, to better understand how water and ices shape the evolution of a body. We visited both Vesta and Ceres, so now we can compare them. Vesta was confirmed to contain very little water. This is in stark contrast to Ceres, an object which formed in the outer solar system and has abundant water and ices. This indicates that the location an object forms at is critical for determining its water abundance. Even though Ceres held on to its heat long enough to retain geological activity, it still cooled quickly enough that it only achieved partial differentiation, where Vesta, a rocky body, could not cool as fast and was able to achieve full differentiation. This indicates that water plays an important role in determining the heat and therefore evolution of a body. In summary, Dawn represents major achievements, both in spaceflight technology and in planetary science. Dawn embodies the beginning of an era of space travel where spacecraft can operate longer and not just visit, but orbit multiple bodies. Dawn found that the location of formation of a body is critical for determining its composition, but the current location of an object may not be the location it formed at. There is now increasing evidence that significant shuffling events occurred in the early solar system. Dawn found water plays an important role in the evolution of objects, and high water abundance may hinder differentiation. Differentiation may also be much more common in the evolution of large rocky protoplanets than was previously thought. Dawn also found evidence that salts can extend the period of geological activity in water-rich bodies that otherwise would have cooled and frozen. Thank you for taking the time to explore just a little bit of the solar system with Dawn.